Assalamu alaikum. Hello, guys. Today we will cover chapter 4 and it is numerical computation. Let's get started. Okay, so today we will cover chapter 4 numerical computations. It is, like a very important topic actually. And today we will talk about gradient descent, about overflow, underflow. And in next video, we will do practical session where we will draw this kind of plot of gradient descent. Please check my next video in this series of videos. So first of all, let's cover overflow and underflow. It is very fundamental thing, and overflow happens when calculation result in a value that is too large for a data type to represent it. Okay? I'm repeating again. So it happens when a computer uh, cannot cannot represent that amount of number with its data type, and it fails. As it fails, it will round it. So maybe if the number is too large, and the computer will say just it is infinite number. If your number is very small, 0.000 and some kind of bunch of zeros and 1, and if your computer, if your programming language data type cannot represent it, it will say just it is 0. So it creates a problem. So problem, we call it rounding error. So it's saying that rounding error is problematic, especially when it compounds across many operations and can cause algorithms that work in theory to fail in practice if they are not designed to minimize the accumulation of rounding error. So overflow and underflow are the same. So if you make one calculation and it makes a very huge number, and that huge number cannot be represented with your data type, it is overflow. The same, if the calculation counts very small number, 0 point, a bunch of zeros and 1, and your data type cannot represent it, and computer will say it is 0 and 0, just 0, it means underflow. So uh, for for understanding it much more better, so let's go to let's make one code. Okay, so let's I will activate IPython. So here it is Python, it's just normal Python, but it's in terminal. So I have IPython. So the data type, maybe it is int or it is float, it depends. I assume you know that if I say like that, it is float. Okay, if I say x equal to 3, it is integer. Okay, something like that. And in Python, the maximum number, the integer this int data type can represent is it was, if I don't mistake, 3E308. Okay. So yeah, so if I say x equal to 1E308, this is very big number, like maximum of Python integer to represent. So if I say type x, it is saying float. Okay, doesn't matter. Okay, this is float. Okay, we are getting this float, and 1E308, it means 1 multiplied to 10 powered 308. So that's a representation. So if I say, so it is saying that 1e plus 308, it's the biggest number. And for example, if I say x multiplied by x, if I multiply this x to another x, the same number, over itself, I'm receiving y. And if I print y, it is infinity. So now what's happening? So actually, this is very huge number, but it is still number. I take that number and I multiply itself to itself, and I am getting bigger number. And computer saying that it is infinity, but actually it is not infinity. So that's the problem of overflow. And sometimes because of this kind of problem, the algorithm works in theory, but in practice it fails because of this kind of small details which fails, that data type cannot represent. And it is about Python, right? Python standard data types. We have, in Python we have NumPy. So in NumPy we have np.float 32, and for example, I can put some kind of number like 1e45 maybe. Okay, it's saying it's overflow. Yeah, now it's saying, for example, if I put 100, so it's saying me 100, and float 32 means specific data type that has specific range from minus something to plus something. And we have np.float 64. We have 182, 28, 256, I'm not sure. Okay, we don't have that. But the point is that when you doing that some kind of calculations, and you don't want to face overflow, underflow, you should be careful that if you are using Python standard libraries, you may get overflow and underflow, which results in inaccurate performance of your algorithm. So if you use NumPy, or if you use specific precisions, specific float 32 or float 128, by using this, you will solve the problem, and you will not face this kind of problem of overflow and underflow. So that's the basic introduction. So you understood about overflow and underflow. So overflow, it means computer says just infinity. Okay, if it's very huge number, it cannot represent, it will say infinity. If we put very small number, so if I put x equal to np.float 32, in float 32, the smallest number, which means 0 point something 1, it is 1e minus 45. So this is the smallest number as float 32 can represent. So if I print x, so that's the number. If I now we will make one trick, that we will say x divided, or we will say x multiplied, it's better, x multiplied to the highest number, float 32, mp float 32 1e45, and we are getting overflow. Okay, so if I print this y, I am getting infinity. Okay, now I am getting infinity. If I redo again, I say smallest to smallest. In other ways, I will do x by x. I'm getting y. If I print y, it is 0. Actually, it shouldn't be 0. So it should represent very small number, but here we are getting 0. So that's about underflow. Underflow means the number is very small and we give it, and computer says that it is just 0. So that's one thing we should care about in numerical computation: overflow, underflow, and overflow. I think that's enough for this thing. And another thing is poor conditioning. Conditioning or poor conditioning refer to situations where small changes in the input to the function leads to large changes in the output. This typically occurs in metric calculations, and we define condition number as the magnitude, as a ratio of magnitude of largest eigenvalue to the smallest eigenvalue. The conditional number, the range of condition number is from 1 to infinity. If by getting the ratio of largest to smallest eigenvalue, you are getting the number 1, result as 1, it means it is well conditioned. That it means small changes in the input to the function doesn't make big changes in the output. It means well conditioned. If you are getting numbers larger than 1, it means it is going to be poor conditioned. That if you make small changes into the input to the function, which might lead to the big changes in the output. That is another consideration when we are implementing algorithms, specifically machine learning algorithms in practice. So that's second thing we should think about. Yeah. And the third thing is gradient-based optimization. So I think you may come across with these things. And yeah, so let's cover it again anyway. Most deep learning algorithms involve optimization. The famous optimization is, we call it gradient descent. And gradient descent is first order iterative algorithm, optimization algorithm to use for finding minimum of a function. So optimization means minimizing or maximizing some function, and gradient descent minimize a function. So some notations. So we can say that function we want to minimize or maximize is called objective function or criterion. And when we are minimizing it, we may also call it cost function, loss function, or error function. We mostly call this loss function, but it depends. It doesn't make big sense, big change. So what we should talk? Okay. Here I want you to explain derivative and gradient descent in theory. So we have saddle points. Okay, so let's start with gradient descent. I will switch my screen, webcam. Okay, so I have camera. So I think you hear me well. So derivative, if we talk about derivative is it represents the rate at which a function changes as its input changes. And derivative is has a formula like this, and it is that fx plus h minus fx by x. Okay, I think you can see. Yeah, here. So what we are doing here is that this is a general formula for derivative,
and the derivative at function fx at a certain point x, it measures how this fx function increases or decreases as x input value increase by the infinitely small amount. It tells the slope of the tangent line at any point of the function. So derivative, we can prove derivatives of some common functions. For example, if there is one function, if for example we have function like x square, the derivative of this function is 2x 2 minus 1, which means 2x. And there are some more formulas about derivative. But the point is that why we care about derivative is that derivatives helps us to find the gradient descent. So gradient descent is that x, if I write here, okay, gradient descent is that it is x equal to x minus error, and this notation fx. So gradient descent is that it is iterative optimization algorithm used to find the minimum of a function. So this is a learning rate. This is a previous x, this is resulting x, and this is function, the derivative. And it depends on the function. So if we give some kind of function and we find the derivative and we put derivative here. So for example, let's use one function fx and y. If we give two input, and if x plus xy plus y squared. So assume we have this function. So gradient descent of this function with respect to x is that derivative x, derivative of f to derivative of x equal to, with respect to x, it means we will ignore this y. So it will be 2x plus y. So what we did here is that we found first order partial derivative of this function with respect to x. It means just finding the derivative. If we will find derivative of f function with respect to y, it will be, we will not use x, we will think about y, and it will be x plus 2y. So it's both, it means first order derivative, first order partial derivative. So there is another term, derivative. We have derivative and we have partial derivative. If a function has multiple inputs and we want to find one of the input of this function, we will use partial derivative, or it's just called partial derivative. If a function gets only one input, it is just a normal derivative. So if, for example, fx equal to x cubed, so if we want to find this derivative of this function and it has only one input, it will be just derivative. But if we want to find derivative of this function with respect to x, it will be partial derivative. That's all about partial derivative and about derivative. And there is also two things: first order partial derivative and second order partial derivative. first order partial derivative means that we are just finding the partial derivative. But second order partial derivative means we are finding derivative of the derivative. So for example, this is first order, and we want to find second order. Second order of this function will be second order. We will note it like this. With respect to that x, it will be what? So we will find just the derivative of derivative. If we find derivative of this derivative, it will be 2. If we want to find the derivative of the function with respect to derivative of x and derivative of y, so it means if we will find the derivative with respect to y, here it will be just 1. So this call is second. Okay, I think you can see it. Okay, second order partial derivative. First order why we are thinking about why we are taking care about this first order and second order. So
the point is that gradient descent uses first order, but if you will read this chapter, and if there is the terms, there is a small section which talks about Jacobian and Hessian matrices. So these matrices uses second order derivative and a partial derivative or first order partial derivative. So understanding this first order, second order is important for these matrices. So we are saying that the Jacobian matrix, as I understood, it is a matrix of first order partial derivative of a vector valued function. So it's a matrix of first order partial derivative of vector valued functions. And so I think that's all about it's about Jacobian matrix, and that's what I understood. And there is also Hessian matrix. Hessian matrix is second order. So it is second order partial derivative. It's a square matrix, first of all. It is square matrix of second order partial derivative of scalar valued function. That's basically what I understood from this text. And I think that's all about today. So there are some cool graphs. You can to look them. So in a practical session, in next session, we will try to write code for plotting these graphs of how the function is learning. So gradient descent is very interesting in practical. So in next video we will do that. So that's enough for today. So see you on next videos. Bye bye.